Hey there, Loz Blaine here for Gizmag, and today we're talking transmissions with a fellow who reckons he's invented the holy grail of power transfer. It's an infinitely variable transmission, so it can smoothly transition from reverse through neutral all the way up to top gear, so you're always in a perfect gear for maximum efficiency. But unlike most CVTs, it doesn't use any friction components. All the power is transmitted through toothed gear systems, so it can handle huge amounts of torque. This could really be something pretty special. It's a potential revolution in transmission technology. So let's meet the man.
My name's Steve Durnin, and I'm the inventor of this device, which we call D-Drive. What you see is the culmination of thousands of hours that I've spent doing this, in addition to working as a plumber and now as a plumbing inspector. It's my very first attempt at inventing or patenting anything, and it's a journey that has taken me more than 20 years to get to this stage.
This stage is a working demonstration prototype of the D-Drive, an emphatic win on the ABC's New Inventors Show, and a great deal of interest from people in a number of fields who see the D-Drive as an efficient and robust transmission for a variety of purposes. Let's take a look at how it works, and we better warn you, this is a real brain bender. With most transmissions, you can easily see where the gear ratios come from. You'll have small and large cogs, for example, or in the case of a CVT, there'll be some sort of ramp or a slope. With the D-Drive, there's nothing of the sort that you can look at. Instead, the ratio of input speed to output speed is determined by the relative speeds of these two spinning shafts. As you slow one down, the other one speeds up. When you lock the bottom shaft so it's not moving, the top shaft there spins at top speed and power gets transmitted from the input to the output at the device's maximum gear ratio. But when you rotate the bottom shaft in the opposite direction to the top shaft, which in this case is done using a small electric motor, you begin to lower the gear ratio, and once the bottom shaft reaches the same speed as the top shaft, the transmission effectively goes into a zero ratio, or a powered neutral. If you accelerate the bottom shaft even further, the transmission will go into reverse, and all with the input motor running at a single optimal speed. It's a bit easier to visualise if you look at the output side. So here we are in full forward ratio with the lower shaft connected to that middle sun gear there, fully stopped. Because that's not moving, the planet gear with the output crank connected has to move around it at top speed in order to keep up with the ring gear on the outside, which is driven by the top shaft. Now let's speed the lower shaft up, which rotates that sun gear. The output planet gear now doesn't have to move as fast to keep up with the pace being set by that outer ring gear, so the output slows down. And if you speed that lower shaft up faster than the top one, the top shaft and the ring gear come to a stop as the planet gear starts circling in the opposite direction, which gives you a reverse ratio. So it's simple. The input shaft drives a ring gear that's eccentrically mounted in an orbital gear. The back of that ring gear drives the bottom shaft as well as sun gears on both the input and output sides. On the input side, there's a rigidly mounted planet gear driven by the first sun gear sitting inside a ring gear that's able to revolve. That revolving ring gear drives the top shaft, which goes through to the output side and drives another revolving ring gear on the output side, and the output crank is driven by a planet gear, whose rotation around the center axis is determined by the relative speeds of the two shafts. Duh! Let's hear Steve talking us through the change of ratios again.
In the present mode, what is happening is it is in neutral. So that when you look at this end of it, the input is turning, but this gear, this large gear, is not revolving. What is happening is there is no output here, and both of the shafts are being equal. When we input, or when we slow this bottom one down, what will happen is that the device will actually start to rotate in a clockwise direction, and we call that full speed forward. So now at that stage there is no input from any other source other than the engine coming in here. This is stop, this is going faster, this is full output. Now what we'll do is bring it back to a powered neutral by speeding up the bottom shaft, which is this one down here. We'll speed that up to the point where we now have no output. Everything is stationary on the front, the engine is still turning, and as we speed this bottom shaft up, you'll observe the top shaft actually slowing down to the point where we now have a reverse situation. So what is happening is that the planetary gear is being carried around the ring gear, it's being driven by the sun gear, and we have full speed reverse.
To understand what's so good about the D-drive, you need to think about the deficiencies of other transmission systems. Most systems that use gears have a number of fixed ratios that you have to choose between. Plus, you need to disengage and re-engage the gears using a friction clutch. Most variable ratio systems are based on friction, which means that if you put too much power through them, they'll start to slip. With the D-drive, the ratio is infinitely variable, so you can always have the perfect gear ratio, and the power is always being transmitted through strong, reliable gear teeth, so it's never going to slip.
It's not like a belt drive where you have a V-belt that operates between two pulleys that vary their size, or a toroid, which is a plate that operates between two curved discs. It is the pressure of the plates being pushed together, or the discs being pushed together, that cause the change in ratio, but at all times it is a flat surface pushing on another flat surface. This is why they're limited in the amount of torque that you can put through them. In theory, and it is at this stage theory, we should have a system of gears here that, depending on the size that you manufacture them to be, that will be the limiting factor of the amount of power that you can put through it. Because your torque should be unlimited because it's gears. The bigger the gears, the more torque you can put through it.
But what about the efficiency? After all, unless you're in top gear with that bottom shaft locked, you need to be putting energy into that bottom shaft to spin the thing up. But that energy doesn't have to be anywhere near the energy that you're putting into the input drive, because it doesn't have to work against that power. All it really has to do is rotate those planetary gear systems around one another to affect the final ratio.
This prototype uses a small electric motor to do that job, but Steve envisions a number of other potential options.
This would work very well if we had an internal combustion engine on this end and electric motors here, for example. We would have a hybrid drive. It could be done with a kinetic energy recovery system where they drive weights and a flywheel. It will do the same thing. You're actually storing energy, and then you can input it back into the system to vary the speed. It can be done hydraulically. There are a variety of ways that it will be done.
So the real selling point for the D-drive is going to be how efficient it is when it's fully prototyped and tested. How does the energy input into those control shafts compare with the energy losses of a friction clutch, or a manual gear system, or a conventional CVT? Steve's very cautious never to say anything that he can't back up, but he's quietly confident.
We've been having discussions with an engineering company who have examined this and find the principle to be sound. They think that it will be quite fuel efficient in terms of what it can achieve if it were to be put into a vehicle. What we will do is build a device that is not made of plastic. This was a model that we built just to prove the concept. We will have a system of a metal gearbox where all the shafts are held true. We'll have a torque measuring device to find out how much energy we put in, how much we have to take out to vary the speed, and we'll measure the output, and we'll have a defined result. I believe that when we've done the testing, this will be proven to be an order of magnitude more efficient than the existing variable drive systems.
This is the first time Steve's gone through the process of patenting and trying to commercialise an invention, but the potential advantages of the D-drive are enormous, and the potential market applications are simply colossal. Everything from cars, bikes, boats, trucks, tractors, heavy machinery, big marine stuff, even wind power generation. So the engineering world's going to be watching Mr. Durnin's next steps very carefully, and with a bit of luck, plumbing inspections might end up being the last thing on his mind.